We're getting close to the last few sections of our linear algebra class here. So our next section is 5.5, and then we've got 4 sections of chapter 6. Okay, so 5.5 is complex eigenvalues. So when we talked about eigenvalues to this point, we've talked about real numbers. Okay, we've said that those were the situations we were looking at where we have a real number where we can do ax equals lambda x, or ax minus lambda x is equal to 0, and then determining what the corresponding vectors are that go with that equation. But as we know, when you have a quadratic equation, which is what you have a lot of times for a 2x2 matrix, you aren't guaranteed a real solution. You many times have a complex solution, or one that involves complex numbers. Okay, so if I have a matrix A, this matrix A is a pretty simple matrix: 0, -1, 1, 0. And I take the determinant of this. Okay, so I'm going to do the determinant of A minus lambda I. Okay, so I'm going to take the determinant here. I'm going to wind up with minus lambda and minus lambda. So I'm going to have minus lambda times minus lambda. And then on the back side, I'll have plus 1, because it'd be minus 1 times 1, and then it's minus because of the determinant formula. And then, as usual, to find the characteristic equation and then to find the eigenvalues, we set that equal to 0. So minus lambda times minus lambda, that's lambda squared plus 1 equals 0, which would be that lambda squared is equal to -1, which we should all recognize from algebra that that's going to mean that lambda is equal to plus or minus I, okay, or an imaginary number. Okay. And so we can use some techniques that we're going to talk about, but I can take my matrix A, multiply it by a complex valued vector here, 1 and minus I. And when I do that, I get I and 1, which we should also recognize then if I do I times 1 minus I, that will yield that same matrix. So this is I, my eigenvector, my eigenvalue, and this 1 and minus I would be my eigenvector. Okay, and I could do the same thing then for the other eigenvalue. If I multiply it by minus I and 1, it's going to give me minus I. Oh, I wrote it down wrong. Let me try that again. Multiply that by 1 and minus I, that's going to give me minus I and 1, which we can also see is negative I times an eigenvector 1 and I. Okay, so again, I just gave you the eigenvectors here for this one. We found the eigenvalues using the same method we found before. And then we're going to go through here how we can find these two eigenvectors. Okay. So naturally then, let's look at an example. Okay, so I'm going to have first up here, a matrix A is going to be 1, -2, 1, 3. Okay, so as usual, I want to do A minus lambda I. A minus lambda I is going to be 1 minus lambda, -2, 1, 3 minus lambda. I'm going to take the determinant of that. The determinant of that's going to be 1 minus lambda times 3 minus lambda plus 2. Right, because you get minus 2, and then it's minus because the determinant, and as usual, we are setting that equal to 0. Okay, so I'm going to multiply that out. I'm going to get 3 minus lambda minus 3 lambda plus lambda squared plus 2 equals 0. Rearrange, so I have lambda squared minus 4 lambda plus 5 is equal to 0. And you should recognize that that doesn't easily factor. So we need to use the quadratic equation. So lambda is going to equal -b, which is 4, plus or minus the square root of b squared, 4 squared is 16, minus 4 times a, which is 1, times 5, which is c. And then it's all divided by 2. So I get lambda then is 2 plus or minus. 16 minus 20 would be a -4. So I get 2i divided by 2. I just get I. So it's 2 plus or minus I. So these are my eigenvalues. 2 plus I and 2 minus I. Okay, 2 plus I, 2 minus I are my eigenvalues. Okay, so we continue then. We find the eigenvectors using a similar technique to what we did before. I'm going to do A minus 2 plus I times the identity. Okay, just like I did A minus lambda I, here's lambda, so we're plugging in lambda. Okay, so I'm going to do 1 minus 2 minus I. So 1 minus 2 is 1 minus I. -2 stays the same. 1 stays the same in the lower left. And then I'm going to have 3 minus 2 minus I. So I get 1 minus I. And then I said minus 1. I didn't write down the negative sign there. So 1 minus 2 is going to be a -1. So -1 minus I and 1 minus I. Okay. And this corresponds to a system of equations, right? Homogeneous system, 0 vector, all that good stuff. So this is going to mean that I have 2 equations here. -1 minus I times x1 minus 2x2 is equal 0. And then I have x1 minus 1 minus I times x2. I said minus, that should be plus, equals 0. Okay, so I have these 2 equations. And the reason I wrote minus, you'll see in a second. I have this set equal to 0, so I'm going to choose the bottom one because it's going to be easier to solve for x1. Okay, x2 has a 2. I'd have to divide by 2, so you can use either one. Okay, there's no rules. They're simultaneous equations, so they both work. Okay, so I'm going to have x1 is equal to -1 minus I times x2. Okay, which is the same thing as x1 being -1 plus I times x2. So if x2 is equal to 1, because that's a nice easy value to work with, x1 would be -1 plus I. So my vector then is x1 is -1 plus I, and x2 is 1. There's my vector. Okay, so I'm going to do the same thing then for A minus 2 minus I. And I know there's an I for imaginary and an I for identity that gets a little confusing here, but just be careful. Okay, so I'm going to do 1 minus 2 plus I now. So I'm going to get -1 plus I, 2, 1. 3 minus 2 plus I, so I get 1 plus I. Okay, so if you compare the 2 matrices here, they are the same except for they're the conjugates of the complex numbers. Okay, so then the same thing's going to happen here with my system. x1, let me try it again, -1 plus I times x1 plus 2x2 equals 0, and x1 plus 1 plus I x2 is equal 0. So the corresponding eigenvector then is going to be that x1 is equal to -1 plus I x2. Means x1 is equal to -1 minus I x2. So my vector is -1 minus I and 1. So if you compare those vectors again, they are just the complex conjugates of one another. Okay, so let's just be careful here. Let's note this was with lambda equals 2 plus I, and this was lambda equals 2 minus I. Okay, and so there's my complex eigenvalues and eigenvectors for that matrix. Okay. All right, so let's look at another one here. Okay, so our next example, which we will call matrix B. Okay, so we're going to have B then. Going to be equal to 1. Oh, done that one, sorry. Let me write down the new one there. There we go. Yeah, I've got 1. Okay, 1, -10, 1, and 7. There we go. Okay, so my determinant of b minus lambda I. That's going to be 1 minus lambda times 7 minus lambda plus 10. And again, we're setting that equal 0. So we multiply. So I'm going to have 7 minus 7 lambda minus 1 lambda plus lambda squared plus 10 equals 0. Okay, so I'll put all that together. I've got lambda squared minus 8 lambda plus 3. Not plus 3, plus 17, not subtracted. Those are added. Equals 0. Okay, so lambda then is going to be 8, because negative 8 negative is going to be positive, plus or minus the square root of 64 minus 4 times 1 times 17, all divided by 2. So lambda is going to be 4 plus or minus 64 minus 68 is going to be 4, but negative. So negative 4 under the square root. So I get negative 2i divided by 2. So I just get 4 plus or minus I. Okay. So b minus 4 plus I. So 1 minus 4 is negative 3 minus I. Negative 10 and 1 stay the same. 7 minus 4, that's going to be 3 minus I. Okay, so again, I'm going to use that bottom equation because it's just x2. So I have x2 is equal to negative 3 minus I x1. I'm sorry, I said that backwards. x1 is equal to negative 3 minus I x2. Okay, I'm using that bottom equation because it's a little easier to write the equation there. Okay, so that means that x1 is negative 3 plus I times x2. So my vector then is going to have 1 for x2 because that's easy to deal with, and minus 3 plus I for x1. Okay, and this was lambda equals 4 plus I. Okay, same process for the others. Minus b minus 4 minus I. Okay, and again, we just get the conjugates. So we're going to get minus 3 plus I, minus 10, 1. We're going to get 3 plus I. 7 minus 4 is still going to be 3. 1 minus 4 is still going to be negative 3. Okay. So again, I'll have that x1 is equal to negative 3 plus I, x2. So x1 is equal to negative 3 minus I, x2. So my vector then is going to be negative 3 minus I and 1. And again, notice that those are conjugates of each other. And this one was for lambda equals 4 minus I. So we use that conjugate property that the middle sign changes from plus to minus or minus to plus. We use that a lot when we're doing complex eigenvalues. Okay. Now, we talked about similar matrices and diagonalization for real eigenvalues. Okay. Well, for complex, we have a similar idea, no pun intended, similar matrices. Okay. So we can write a similar matrix using a theorem and a property. So theorem 9, okay, says that given 2 by 2 matrix A with complex eigenvalues, lambda equals A minus BI, so just a generic complex eigenvalue. So naturally, we know the other complex eigenvalue must be A plus BI, but I know A minus BI. And eigenvector V, then I can write a similar matrix. A is equal to PCP inverse. Okay, we don't want to call it D because it's not diagonal, but we have a similar matrix set up where P is going to be equal to the real parts of V in the first column and the imaginary parts of V in the second column. That's the complex that's the eigenvector. Okay, And C is going to be equal to A minus B, B, A. Okay, remember A and B are your eigenvalue here. Okay, A minus BI. Okay. So the easiest way to remember this is if I look back at my last one here. So I'm going to write down what they were. I had lambda equals 4 plus I. Okay, and I only need one. Notice I only need one set here. With eigenvector V equal to -3 plus I and 1. The easiest way to remember what to do here is you're going to have P. Okay, go to your eigenvector here for P. Okay, read it just like it is. So I have -3, that's the real part, plus 1I, that's the imaginary part. And I have 0, I have 1 for the real part, getting ahead of myself, and 0 for the imaginary part in the second row. So first row, -3 plus 1. Second row, 1 plus 0I, okay? And then C, you take your eigenvalue, in this case 4 plus I, and write it exactly as it reads as well. 4 and 1, 4 and 1I, because remember the formula here is A minus BI, so it makes sense that it's switched around, okay? And then your second row, you're going to switch the sign on that. Notice that the B's here have opposite signs, so that's going to be -1 and 4. Okay? And then you can take your calculator and type in your matrix P and your matrix C and multiply them, and you get exactly the matrix that you started with. Okay, so I've already typed those matrices in. You see A, B, A. It's me 1, -10, 1, 7. Okay, so the easiest way to remember what to do here is to just read across. So I've got my vector first, -3 plus 1, 1 and plus 0 on the second row. Eigenvalue then helps you make C, which is also the case when you do similar matrices for a diagonal, right? We put the values on the diagonal and the vectors over here. So my vectors form P and my values form C, but you have to write them accordingly, okay? 4 plus I there. All right, so I got one more example here for this section. Okay, and my last example okay, let's go back to our first matrix that we did, 1, -2, 1, 3. Okay, so look back at that. 1, -2, 1, 3. Okay, so I look back at my matrix A here. We found the eigenvalues and eigenvectors for this. Okay, the eigenvalues, right, were 2 plus or minus I, and I wrote X there. That should be a lambda. Okay, and my eigenvectors then. So when lambda was equal to, just check back on your notes, right? When lambda was equal to 2 plus I had -1 plus I. So lambda is equal to 2 plus I. I have the vector -1 plus I times and 1. When lambda is equal to 2 minus I had the vector -1 minus I and 1. So there's obviously two ways we could write this P and C, okay? So P, I'm going to take my first eigenvector here, okay, and just read it across. I've got -1 plus 1I, 1 plus 0I. And then C, I take the eigenvalue, which in this case is 2 plus 1I. Then your second row, you switch the sign to the -1, and then you switch the position. So here is P and C. Now notice I could also write a P and C. So this P and C goes here. But I could also write a P and C using the second eigenvector. So this would be -1, -1. Again, reading -1 minus I, 1 in the second row, 0 plus I there, okay? And then C, I take the eigenvalue, so that would be 2 minus 1, switch the -1 to a positive. 2 stays the same but goes to the other side of the matrix. So My eigenvalue became C here, and my eigenvector became P there, okay? So you do the same processes, you just have to ground yourself in complex eigenvalues, okay? If you have any questions, a relatively short section, because we know all the tools. We're just saying, okay, we can apply these to complex numbers. If you have any questions, please don't hesitate to contact me. And we will start talking about chapter 6 next time, which is about orthogonality, okay, and distance between vectors, okay, because you think about what a vector looks like. It's not a single point. So measuring distance is kind of weird, okay? So we're going to be talking about orthogonality and some properties that we get from orthogonality, in addition to another way of doing matrix factorization. We did LU earlier in the semester. We'll do QR factorization at this point in the semester. We also did a matrix factorization here in chapter 5 with the similar matrices, a PAP inverse or PCP inverse, okay? So I'll see you then for chapter 6, which will be our last chapter of the semester, and we'll talk